Hello, and welcome to this presentation, Understanding SCPI. In this presentation, we'll provide a short introduction to SCPI and how SCPI is used for remote control and automation of test and measurement instruments. There are three general ways to control test and measurement instruments. The first is local control, in which the user operates the instrument using the front panel controls and/or graphical user interface. The second is remote operation. In this case, the instrument is operated by means of a program running on a remote PC. This may be a standard remote GUI application, such as VNC or remote desktop, or it may be a dedicated software application. The connection to the instrument is most often made either via Ethernet or USB. The third method, and the one we'll be discussing in this presentation, is remote control. In remote control, the instrument is configured and controlled programmatically, that is, by means of text-based commands that are created, sent, received, and processed via a user-created program. This method is often also referred to as automation, since, unlike remote operation, operating the instrument in this way does not require interactive control by a human operator. There are many reasons for using remote control or automation. The first is efficiency. Remote control does not require a skilled human operator to physically interact with the instrument in real time to make and record measurements. Because the same procedure is used each time a measurement is made, the results are usually much more consistent and largely free of operator-induced variability or errors. In most cases, remote control performs tasks much more quickly than doing them by hand. In addition to controlling an instrument, automation can also include controlling the device under test, and/or other test accessories, such as temperature chambers, switches, etc. And in cases where multiple instruments are needed, the operation of these instruments can be synchronized. For example, if one instrument is used to create and change the DUT input signal, and another instrument is used to measure the changing DUT output signal. Programmatic control also is easily scalable. A test setup can be scaled up or reproduced with very little effort while still maintaining excellent repeatability. And finally, the measurement results can be obtained via remote control and then be logged and processed as part of the remote control program, greatly increasing both accuracy and efficiency. The most common way of implementing remote control or automation is SCPI, which stands for Standard Commands for Programmable Instruments. SCPI specifies both the syntax and the structure of commands and responses used for programmatic control of test and measurement instruments, such as spectrum analyzers, signal generators, network analyzers, oscilloscopes, etc. SCPI specifies the use of ASCII, or plain text strings, that are used to configure, control, and query instruments. It's important to keep in mind that SCPI is a software standard. That is, it doesn't define the physical link, and thus SCPI can be used with many different physical links, the most common being GPIB, Ethernet, and USB. SCPI has numerous advantages. First and foremost is having the same, or at least a similar, message structure for different makes, models, and types of instruments. This makes code more portable between instruments and manufacturers, and reduces the time and effort needed to design automation or remote control. A standard structure also makes SCPI easier to learn, and easier to debug or troubleshoot. Because SCPI uses plain text strings, messages can be composed, sent, received, and parsed using any programming language. For example, Python, MATLAB, C#, LabVIEW, etc. And finally, SCPI helps to facilitate instrument replaceability, since code written for one instrument can either be easily adapted to another, or an instrument may be able to emulate another instrument by accepting the SCPI commands written for that instrument. As mentioned earlier, SCPI works by sending and receiving messages in the form of plain text. We can divide these messages into two groups. A command is typically used to configure or control an instrument when no response is expected. On the other hand, a query does cause the instrument to return a response, most often either the value of a setting or measurement data. Unlike commands, queries end with a question mark. SCPI-compliant instruments should come with a command reference, which describes the commands and parameters supported by the instrument and how they're used. In many cases, this command reference will also provide examples or code showing how to implement common tasks. SCPI messages have a standard format that starts with a header. This header consists of one or more keywords separated by colons. Note that these keywords are often given in mixed case, showing how they can be abbreviated, for example, frequency or just freak. A whitespace character is then used to separate the header from the parameter data. The nature and format of the parameter data will depend on the type of headers. In this example, we're setting the center frequency of a spectrum analyzer to 919 MHz. Some messages will have more than one parameter, and these are separated by commas. Finally, a terminator is used to indicate the end of the message, although this termination is often automatically added by the automation environment or program. Finally, multiple SCPI messages can be sent per line, with each message separated by semicolons. In the remainder of this presentation, we'll walk through a simple example using SCPI and provide more detail on some of the more common SCPI commands. But before we look at an example, let's take a moment to explain remote mode. Many instruments have a special remote mode when being controlled via SCPI. In this mode, the controller has exclusive control over the instrument, meaning that the instrument will not respond to local control. That is, the buttons, touchscreen, etc. become inoperative. An instrument may also use some kind of indicator, an LED or screen message, to indicate to local users that it is in remote mode. Aside from avoiding potential conflicts, another advantage of remote mode is that switching off the local display can sometimes improve the performance or responsiveness of an instrument, since it doesn't need to devote resources to updating the display. It's also worth noting that many instruments have a local button or key that can be used to force an instrument out of remote mode and re-enable local control. Let's now walk through a simple example of controlling a signal generator and a spectrum analyzer from a PC using common SCPI commands. In this example, the controlling PC and the instruments are all interconnected via an Ethernet or LAN connection. But recall that other communications methods or interface types can also be used. The first step is installing VISA on the controlling PC. VISA, or Virtual Instrument Software Architecture, provides a standardized interface between controlling software and test and measurement instruments. The advantage of using VISA is that by abstracting this interface, the same commands can be used regardless of physical interface, such as GPIB, LAN, USB, etc. VISA libraries are available, free of charge, from numerous instrument manufacturers, including Rohde & Schwarz, and are normally available for various operating systems or hardware, such as Windows, Macs, Linux, Raspbian, etc. In most cases, a manufacturer's VISA supports controlling instruments from other manufacturers as well. Installing VISA often includes various useful utilities, such as tools which can display sent and received commands, an interactive command window, etc. Once VISA is installed, test and measurement instruments are specified using a so-called resource name or resource string, which has the basic format of interface type, instrument address, and resource type. For example, a LAN-connected instrument might have the resource string TCP/IP, IP address, instrument, whereas a GPIB-connected instrument would have a resource string that started with GPIB, followed by the GPIB address. We'll look at this again in just a few moments. In addition to VISA, a package or wrapper must also be installed on the controlling PC. This provides user-friendly functions for sending SCPI commands and receiving replies. For example, the write function would be used to send commands to an instrument without expecting a response, whereas query would be used to send a command and receive a response. If Python is being used for automation, the generic PyVisa package can be used. Another option is using a manufacturer-provided package, such as RS Instrument, which provides additional useful features when using primarily Rohde & Schwarz instruments. Recall, however, that Skippy automation can be done using other programming languages, and similar packages exist for MATLAB, C#, etc. In this presentation, we'll show automation examples using Python with the RS Instrument package, but please note that the actual Skippy commands, or strings, are the same regardless of the package or method used to send and receive them. With Visa and a wrapper or package installed, we can now use the resource string and the appropriate package function to create a handle or instance for communicating with our instruments. For example, here we create a handle called SPECAN for communicating with our spectrum analyzer at IP address 192.168.139, and another handle called SIGGEN for communicating with our signal generator with IP address 192.168.140. The package functions write and query are then used together with these handles. For example, if we want to set the frequency of our signal generator, we would use siggen.write and then the Skippy string source, frequency, and the desired transmit frequency. We're using write because no response is expected. If we wanted to read the currently configured transmit frequency of our signal generator, we would use siggen.query followed by source, frequency, ? And the response would be stored in the variable frequency. This value could then be printed, etc., the same as any other variable. Now let's look at some basic or frequently used Skippy commands. These are common commands, source, output, input, sense, calculate, and measurement. We'll start by discussing the so-called common commands. Common commands are standardized in Skippy, and all of these commands start with an asterisk. One example of a common command is RST, or reset, which is used to return the instrument to its default state. It's often a good idea to do this at the start of a program. Another example is the IDN, or identify query, which causes the instrument to return information about itself. This information typically includes the manufacturer name, instrument model, serial number, firmware version, etc. IDN can be used to test connectivity to an instrument and/or to ensure that the automation environment has been correctly configured and installed. Most of the other common commands are used for controlling program flow and command response synchronization, and some of these will be discussed a bit later in this presentation. The source command is used to configure an output signal, and therefore is most commonly used in signal generators. Common parameters include the frequency of the generated signal and output power, as well as any modulation parameters. Note that when configuring AM modulation for this particular generator, we also must specify the source of the modulating signal and must explicitly enable or turn on modulation. Closely related to source is the output command, which enables RF output of the generator. Other output commands can be used for things such as enabling attenuation and protection functions, or for setting output impedance. Input commands are used on the measuring instrument side, such as with spectrum analyzers, and they adjust parameters involved in conditioning a signal as it enters the instrument. A common example is enabling or disabling automatic attenuation, or manually specifying the amount of attenuation. Filtering is another common form of input signal conditioning. Input is also used for port parameters, such as setting the port impedance, or configuring whether the port is AC or DC coupled. Sense also applies to measuring instruments, and differs from input in that sense is used to configure the parameters used to make measurements. In the case of a spectrum analyzer, these would be things like center and span, resolution bandwidth, and video bandwidth. Sense can also be used for configuring the parameters of more complex measurements, such as noise-power ratio or adjacent channel leakage ratio. Calculate commands are used to obtain numerical results when making measurements of signals. That is, they're designed to return a value that's calculated from the result of a sweep or measurement cycle. This means that calculate is used in particular to obtain values associated with markers, limits, and/or statistical values. In this example, calculate commands are used to activate an AM modulation depth measurement, search for the carrier and the sidebands, and then retrieve the numeric AM modulation depth result, which is then displayed to the user. Note that calculate can be used both with write type and query type functions. Measurement is another command that can be used to configure measurements and retrieve data. This command is similar to the sense and calculate commands we just looked at, and is more common on some types of instruments or on some manufacturers' instruments than others. Let's look at an example of how to obtain the frequency of a signal measured on the first channel of an oscilloscope. The source is defined as channel 1, and then the measurement type, here frequency, is configured. A query is then used to obtain the measurement result, which is then printed on the screen. As we can see from the previous examples of sense, calculate, and measure, there can be substantial variation in standard SCPI commands between manufacturers, and even between instruments from the same manufacturer. This difference may be how these commands are used, and in some cases these commands or usage may also change over time. That is, subsequent generations of instruments may use different commands than previous generations. For example, the command configure is sometimes used for setting measurement and/or instrument parameters. The commands fetch and read are often used for querying the results of a measurement on older instruments. And as mentioned earlier, in some cases, different commands may be used to accomplish the same configuration or measurement task. When in doubt about the correct command to use, it's always best to consult the programming guide or command reference for a given instrument. One final topic that's important for SCPI programming is measurement synchronization, which is used to ensure that the instrument is in an expected or known state when it receives an instruction, particularly at important points in the program. The reason synchronization is necessary is that it takes a finite and often non-fixed amount of time for an instrument to process a command, for example, a long sweep or acquisition. It's therefore best to wait for one command to finish before sending more commands. Otherwise, the results may be incorrect or invalid, or the instrument itself may end up in an unstable state. One solution is inserting fixed delays in the program, but this is poor programming practice, since it's both unreliable and inefficient. The preferred or recommended method for achieving synchronization is to have the instrument explicitly inform the controller when an operation is completed. There are several ways of doing this in SCPI, but the simplest and most common is the SCPI command OPC, or Operation Complete. The OPC, or OPC query, blocks the program until a response is received from the instrument. The instrument will only respond after all pending operations have completed. The OPC command is often appended to another command, but can also be sent separately. For example, here we configure our spectrum analyzer to perform a single sweep, and set the sweep time to 5 seconds. The command to start the sweep, init, is followed by an OPC, in order to give the SpecAn time to complete the sweep before performing additional configuration or measurement tasks. Note that a separate user-configurable visa timeout can be defined as well. This timeout can be used to avoid locking up the program if no response is received to an OPC. It's also worth noting that some packages, such as RS Instrument, can be configured to automatically append an OPC to each command, rather than requiring the programmer to add one at each step. Let's end with a brief summary. SCPI is a standard set of commands and syntax used for remote control and automation of test and measurement instruments. In SCPI, text strings are sent and received in order to configure and control instruments, as well as to obtain configuration and measurement values. SCPI commands consist of both keywords and parameters, and the list of supported commands and parameters, as well as usage examples, can usually be found in the instrument's command or programming reference. Before sending and receiving commands, both Visa and an automation package must be installed on the controller. In this presentation, we briefly covered some of the more basic SCPI commands, including common commands, source, output, sense, etc. We also very briefly talked about the importance of synchronization, which is usually implemented by means of the opc command. Lastly, even though SCPI is a standard, there can be substantial variation between SCPI commands from different manufacturers, or even among instruments from the same manufacturer. This concludes our presentation, Understanding SCPI. If you'd like to learn more about SCPI or test automation, please see the links in the video description. Thanks for watching. Please subscribe to our YouTube channel and visit us at rody-schwartz.com.